The day that somebody decided to throw the telephone wire over the wall, giving way to data technologies, was one of the most amazing turning points in our networking industry. Suddenly, voice technology became data technology, giving us the ability to communicate worldwide using a variety of mediums. Even more significant in today's day and age is the ability to eliminate the wires altogether, to be able to communicate using wireless technologies. My name is Mike Storm, and I've been in the networking industry now for about 16 years, very focused on emerging technologies in today's converged internetworks. And one of the things that I find extremely interesting is the use of wireless networking. It's my job and my goal to be able to teach you how to properly plan, design, implement, troubleshoot, and probably most important, secure today's wireless networks. One of the best things that you can do when you're searching out good information about wireless networks is to try to focus on a vendor-neutral program. That's exactly what this series focuses on, is the CWNP certification program. CWNP is an industry leader in identifying and being able to certify individuals on the appropriate wireless networking skills. The CWNP certification program is really intended for individuals who do a full range of things with 802.11 compliant networks: administration, installation, design, even advanced support. The CWNP program is also vendor neutral. What's nice about this is that you will get an opportunity to see a variety of vendors' equipment, not just focused on one single vendor. In fact, candidates that achieve the different levels of CWNP will be trained and qualified to administer and support all of the different brands of wireless LAN hardware. This can be very beneficial, especially in a large enterprise where you do have quite a bit of diversity in the hardware that you use. In our particular series, we're going to be focused on the first level of CWNP certification, the administrator. The administrator's focal points are site survey, installation, and management of 802.11 compliant wireless LANs. Really, the main focus here is that we really understand how 802.11 wireless networks function, how to properly calculate how they should be deployed, and understanding exactly what's necessary to be able to implement 802.11 networks in any given enterprise, from very small to very large. In addition, you can advance yourself into the security professional, which is focused on the design and implementation of 802.11 security techniques, the security processes involved, hardware which can enhance security, as well as specific security software designed to help you to secure your 802.11 network. The CWNP integrator will design and manage wireless LANs, as well as being able to implement quality of service, go through advanced site surveying, advanced radio frequency theory, as well as what's known as vertical market analysis of 802.11 compliant wireless LANs. This is a very advanced certification, but can really help that small set of individuals in a large enterprise who are fully responsible for not only the current deployments of 802.11 wireless LANs, but also looking towards the future on how that network will evolve to keep up with the latest technologies. And finally, the expert level certification, which focuses on advanced packet analysis and troubleshooting using the latest software tools for 802.11 networks. Now, in our case, we're going to be focused on the first level, the Certified Wireless Network Administrator. This focuses on the techniques and the tasks that are vital to really getting the network off the ground, being able to perform the installation, understanding how to manage the 802.11 network, as well as provide ongoing support. We're going to focus primarily on the objectives of the CWNA certification exam. There are several different components that make this up that you're really going to need to understand to have success as a certified individual. Now, whether you obtain certification or not, all of these techniques and processes that we learn in this series are going to be very important to your introduction to 802.11 wireless networking and how you can apply these technologies to a true implementation. The material in this course does come from a variety of very well-known sources. First and foremost, we have the IEEE, the governing board which governs the 802.11 standard. The Federal Communications Commission, which of course governs the way that all of our communications are going to be used when we deal with wireless. The IETF, or Internet Engineering Task Force. Air Defense, which is an excellent website for obtaining specific information about a variety of vendors' equipment. Cisco Systems, who does have a full line of 802.11 wireless networking gear. And of course, the CWNP, or Certified Wireless Network Professional themselves, who produce the exam objectives for this particular series. NetStumbler and Kismet, two additional tools that can be used to help you to identify wireless networks that are out there, unknown or rogue, and also to be able to shut them down to make sure that you can keep your environment secure. Bits and pieces of this series are going to come from all of these areas. I want to make sure that you have the most recent information possible from the IEEE and the FCC, that you understand exactly what is necessary to truly deploy an 802.11 network without violating any laws, as well as making it very functional for your network enterprise. Keep in mind that if you are planning on certifying with the Certified Wireless Network Administrator, you are going to have to make sure that you do understand several key elements. The first thing is going to be the fundamentals of radio frequency behavior, understanding how gain and amplitude and reflection and refraction and all these different characteristics of radio frequency behave in an environment will help you to understand how you can deploy this type of wireless network. Also describing the features and the functions of all of the wireless LAN components, from wireless access points all the way down to the client, or even high-end wireless gateways. Also having the skills needed to both install, configure, and also to troubleshoot wireless LAN hardware, all the peripherals and the protocols that may be in use on a wireless network. To be prepared to tackle this series and to have good success, candidates that begin this series should already have completed the CompTIA Network Plus certification, the Cisco CCNA, and a Microsoft MCP certification, or at least have equivalent knowledge in all three areas, as we are going to be covering some very advanced networking concepts. There are a lot of assumptions that are made that you already understand how the base internetworking components function together. Because we're going to be putting wireless networks right on top of an existing network, it is very important that you have a solid understanding of how your current internetwork infrastructure is functioning. And that will allow you to have the best success with this CWNA series. In order to properly cover all of the required information for the CWNA, we're going to have to focus on several key areas. First and foremost is a good understanding of radio frequency technologies, the fundamentals behind RF, as well as the mathematics that are used to calculate radio frequency, and finally what spread spectrum technologies are all about. We also need to understand wireless LAN technologies, both the 802.11 networking architecture, as well as the physical and MAC layers of wireless LANs. In addition, wireless LAN implementation and management is something of key importance to most individuals who really need to implement an 802.11 network. And it is very important that we do understand the wireless LAN application in a given network environment, how hardware management is going to become a major part of our job description, how we troubleshoot wireless LAN installations, and also how we conduct a radio frequency site survey. It's also very important, especially in today's day and age, that we are able to implement our wireless networking in a secure fashion. So we do need to understand wireless LAN security, how to protect ourselves, what types of attacks exist out there so that we know some prevention techniques, and finally what security solutions are available to us at this level. It's also very important, especially for the CWNA exam, that you do understand the wireless LAN industry and its standards. We do need to focus on the standards themselves that govern how the 802.11 components work together, and also what organizations are involved and what regulations they set forth to keep everything intact. Remember to focus on what's important for this level. Even though you can take just about everything that we cover in this series to a much greater depth, our focus is on a good, solid understanding on how all of the radio frequency technologies work together and how we can actually apply those to a given network scenario. It is very important that as we go forward throughout this series, that we always stay focused on the 802.11 standards and that everything that we do does in fact comply with FCC regulations. That's going to be a very important point, and you can expect to see a lot of information about that anytime you're dealing with vendor-neutral equipment, as every bit of equipment is going to operate just slightly different. So where do all these technologies come from? Why is it that just now we're starting to see a wide acceptance of wireless LANs? Why is it that companies are beginning to adopt this almost as fast as they adopted Ethernet originally? Well, there is some history behind wireless, some significant events that have occurred throughout our industry's history that have actually allowed this to become a more cost-effective solution and also have really elevated this into a more secure standard. What we're going to need to do now is to take a look at the history of wireless networking. The market for wireless LANs actually seems to be evolving in a similar fashion to the overall networking industry, starting with the early adopters using whatever technology was available to them. The market has moved into a rapid growth stage for which popular standards are really providing the catalyst now for wireless LANs. The big difference, though, between the networking market in a whole and the wireless LAN market is really the rate of growth. Wireless LANs allow so many flexibilities in their implementation, it's really no wonder that they're outpacing every other market sector in today's day and age. One of the major elements is spread spectrum technologies. Spread spectrum wireless networks, like many technologies, came of age under the guidance of the military. The military needed a simple, easily implemented, and secure method of exchanging data in combat environments. And as the cost of wireless technology declined and the quality increased, it became cost-effective now for enterprise companies to integrate wireless segments into their network. Wireless technology today really offers a relatively inexpensive mechanism for corporate companies to actually connect campus buildings to one another without having to lay additional copper or fiber cabling. Today, the cost of wireless technology is such that most businesses can afford to implement segments in every area of their network, if not even completely converting to a wireless network overall. This saves the company time and money while allowing the flexibility of roaming for their customers and users. In addition, households are also benefiting from the low cost and the subsequent availability of wireless LAN hardware. Many people are now creating cost-effective wireless networks at home that do take advantage of the convenience of mobility, even creating home offices or wireless gaming stations. As wireless LAN technology improves, we also see the cost of manufacturing of the hardware continuing to fall, and the number of installed wireless LANs will continue to increase as a result. The standards that govern wireless LAN operation will increasingly stress interoperability and compatibility, so it is a very important factor to understand, because as the number of users grow, lack of compatibility may render a network useless, and the lack of interoperability may interfere with the proper operation of other networks or even possibly other devices. Because wireless LANs transmit using radio frequencies, wireless LANs are going to be regulated by the same types of laws that are used to govern such things as AM/FM radios. The first standards organization which is responsible for this is the FCC, or the Federal Communications Commission. They regulate the use of wireless LAN devices. In the current wireless LAN market, there are several accepted operational standards and drafts that are in the U.S., and those are created and maintained by the Institute of Electrical and Electronic Engineers, otherwise known as the IEEE. These standards are created by groups of people that represent many different organizations, including academics, business organizations, military organizations, and even the government. Because standards set forth by the IEEE can have such an impact on the development of the technology, the standards can take many years to be created and to be agreed upon. And probably one of the first standards that we see that deals directly with wireless is 802.11 itself. This is the original wireless LAN standard that does specify the slowest data transfer rates in both radio frequency and light-based transmission technologies. This standard was ratified by the IEEE in 1997. We also have seen IEEE 802.11b, which describes a somewhat faster data transfer rate and a more restrictive scope of transmission technologies. This standard is also widely promoted as what's known as Wi-Fi by the Wi-Fi Alliance. This standard was ratified by the IEEE in 1999 as an amendment to the original IEEE 802.11 standard. IEEE 802.11a describes a much faster data transfer rate than 802.11b, but it does lack backward compatibility with 802.11b. It uses the 5 gigahertz UNII frequency band, and this standard was ratified by the IEEE in 1999 as an amendment to the original IEEE 802.11 standard, very much like 802.11b. Probably the most recent draft that we've seen is the 802.11g standard. This is based upon the original 802.11 that describes the data transfer rates equally as fast as 802.11a, but it does boast the backward compatibility to 802.11b, which is really required to make it inexpensive and allow upgrades to occur in most network environments. Emerging technologies in addition to these 4 primary standards that are set forth by the IEEE will require that the standards describe and define proper behaviors. The challenge for manufacturers in the future and the standards makers alike will be bringing their resources to bear on the problems of interoperability and compatibility. We do see a lot of future standards that are beginning to evolve, and I would challenge you to use the Google website to actually look at some of these new standards, such as 802.16 and 802.20. 802.16, which is very focused on what are known as wireless metropolitan area networks, which can actually increase the range of a single access point to upwards of 30 miles. And 802.20, which really follows similar standards, but also allows no signal loss at over 130 miles per hour, making it possible for us to actually have wireless technologies wherever we go, even while traveling interstate. So it is very important to keep track and keep up on the future standards and really look into this stuff to identify how this is going to benefit you in the future. Another major factor that we have in identifying what wireless LANs are all about is the application of wireless LANs. Now, we are going to have three main roles that we see with applying wireless LANs to our network environment: the access role, the network extension role, and building-to-building roles. The first one that we see is the access role. Now, wireless LANs are mostly deployed in the access layer role, meaning that they're used as an entry point to the wireless network. In the past, access has always been defined as some sort of a dial-up or ADSL or cable or some other type of connectivity. But wireless is just simply another method for users to access the network. Wireless LANs are data link layer networks like all of the other access methods that you would use. But due to a lack of speed and resiliency, wireless networks are not typically implemented in distribution or core roles in networks. Of course, in small networks, there may not be a differentiation between core, distribution, or access layers of the network. And however, we look at larger networks, we see that the core is always going to be focused on being fast and reliable, very stable, being able to handle a tremendous amount of traffic with little difficulty and experience absolutely no downtime. And that's not what wireless technologies are all about in a larger company. So wireless LANs do offer a specific solution to a difficult problem, primarily mobility. Without a doubt, wireless LANs solve a host of problems for corporations and home users alike. But all of these problems point to the need for freedom from data cabling. And that's really what the access role type of deployment is all about. Cellular solutions have been available for a long time, offering users the ability to roam wherever they want and still be able to use their telephone. Wireless LANs offer the same flexibility without the disadvantages such as roaming charges and long distance and so forth. Wireless LANs today are also very fast, very inexpensive, and can be located just about anywhere in this role. So when considering wireless LANs for use in your network, keep in mind a few things. You want to use them for the intended purpose that's actually going to provide the best result. Administrators that implement wireless LANs in a core or distribution role should understand exactly what performance to expect before they do so, because you may have to remove them later. The only distribution role in a corporate network that's definitely appropriate for wireless LAN is that of building-to-building bridging. In this scenario, wireless could be considered as playing a distribution role. However, it will always depend upon how the wireless bridging segments are used in the network. The next major category of wireless network is the network extension role. The network extension role really serves as an extension to the wired network. Now, there may be cases where extending the network would require that you install additional cabling that's very cost prohibitive in some situations. You may discover that hiring cable installers and electricians to build out a new section of office space for the network may cost tens of thousands of dollars. Or in the case of a large warehouse, the distance may simply be too great to use Cat5 cable at all for your Ethernet network. Fiber may have to be installed, which does require an even greater investment of time and resource. Installing fiber might involve upgrades to existing switches as well. So wireless LANs in this case can be easily implemented to provide seamless connectivity to remote areas within a building. Because little wiring is necessary to install a wireless LAN, the cost of hiring installers and purchasing Ethernet cable might be completely eliminated from the equation. The third type of application for wireless LANs is that of building-to-building connectivity. In a network campus environment, as few as 2 adjacent buildings might need to be connected to allow users of the same environment to be able to connect to the same network. Now, in the past, this type of access was normally accomplished by running some sort of a cable underground, such as copper or fiber, or possibly by renting an expensive lease line from the phone company. But using wireless LAN technology, equipment can be installed easily and quickly to allow 2 or more buildings to be part of the same network without having this added expense of lease lines or possibly running your own cable by digging up the street. With the proper wireless antennas, any number of buildings can be linked together on the same network. Now, there are going to be certain limitations to using wireless LAN technology, as there is in just about every data technology that you use. But the flexibility, the speed, and the cost savings that wireless LANs introduce to the network administrator will make this type of connectivity indispensable. In a campus environment or an environment with as few as 2 adjacent buildings, a couple of things that you need to consider. You will have a couple of link options, what are known as point-to-multipoint links, as well as point-to-point links. Now, point-to-multipoint links will be wireless connections between 3 or more buildings, which are typically implemented like hub and spoke and that type of star topological fashion, where one building will be the central focus of the network. The other buildings will interconnect to the main building as spokes. Now, this central building would most likely have the core network that exists in your network environment. All the internet connectivity, possibly the server farm, would also be placed in this location. Point-to-multipoint links between buildings typically use some sort of an omnidirectional antenna in the central hub building and semi-directional antennas on each of the outlying spokes. Point-to-multipoint implementations do differ quite a bit from point-to-point implementations where you only have a few buildings that have to be connected, such as 2, where you'll actually use a semi-directional antenna on both of these buildings and provide direct line-of-sight access building to building. In either case, you're going to have the same type of end result, and that is that users in one building will be able to use the wireless connectivity to gain access to the core of your network. And as you're going to undoubtedly see throughout your career, there are many ways to implement these 2 basic types of connectivity. However, no matter how the implementations vary, they will always fall into one of these 2 categories, either a point-to-point building to building or a point-to-multipoint building to building. Another component that we have to look at is what's known as last mile delivery. Wireless internet service providers, or what are known as WISPs, are now beginning to take advantage of recent advancements in wireless technology to offer what's known as last mile data delivery service to their customers. Last mile refers to the communication infrastructure, whether wired or wireless, that exists between the central office of the telecommunications company or cable and the end user. Currently, the telco and cable companies own their last mile infrastructure, but with the broadening interest in wireless technologies, the WISPs are now creating their own wireless last mile delivery services. Consider the case where both the cable companies and the telcos are encountering difficulties expanding their networks to offer broadband connections to more households or businesses. If you live in a rural area, chances are you're not going to have access to some of the cool stuff like the DSL technologies or cable modems, and probably are not going to for quite some time. It's much more cost-effective for wireless ISPs to offer wireless access to these remote locations because wireless ISPs will not encounter the same costs a cable company or a telco would incur in order to install the necessary equipment required for their last mile delivery. Wireless ISPs have their own unique set of challenges, however. Just like DSL providers do have problems going farther than 18,000 feet overall from the central office, and cable providers have issues with the cable being a shared medium. Wireless ISPs have problems with rooftops and trees and mountains and lightning and every type of atmospheric attenuation you can think of, and also other obstacles are going to have to overcome that get in the way of connectivity. Certainly, the wireless ISPs don't have a fail-proof solution, but they do have the capability to offer broadband access to users that other, more conventional technologies cannot reach. How do we actually use wireless technologies, though, in our varying business scenarios? It is very important that our expectations are appropriate for the way that wireless is really going to benefit us. As an access layer solution, wireless LANs can absolutely not replace wired LANs in terms of data rates. We know that Ethernet operates at 100 megabits per second, 400 base T, whereas 802.11a, the fastest wireless standard that we have, only maxes out at 54 megabits. And that's sometimes only half in some cases. And this means that we're going to be using an environment which uses intermittent connections, has higher error rates overall, and usually a narrower bandwidth. So what's the use? A lot of times the applications and messaging protocols have all been designed for the wired world, and sometimes will operate poorly in a wireless environment. What's interesting is that the wireless expectations of both the end users and the IT manager often are set by the performance of the wired network, and that's something that we have to change. What wireless LANs offer is an increase in mobility as the trade-off for speed and the quality of our services. For example, let's say that a parcel delivery company uses wireless technology to update parcel tracking data immediately upon the arrival of the delivery vehicle. As the driver parks at the dock, the driver's computer has already logged onto the network and transferred the day's delivery data to the central network. In warehousing facilities, as another example, wireless networks are used to track the storage locations and disposition of products. This data is then synchronized in the central computer for future purchasing and for shipping departments. Handheld wireless scanners are becoming commonplace in organizations that do have employees that move around within their facility for processing orders and inventory. But in each of these cases, wireless networks have created the ability to transfer data without requiring the time and the manpower to input the data manually at the wired terminal. That's the trade-off. Wireless connectivity has also eliminated the need for such user devices to be connected using wires that would otherwise just get in the way and be a lot more expensive. So some of the newest wireless technology is really focused on allowing the user to roam or to move physically from one area of wireless coverage to another without losing connectivity at all, just as your cellular telephone is able to roam between cellular coverage areas. In larger organizations where wireless coverage spans very large areas, roaming capability has significantly increased the production of these organizations overall, simply because users remain connected to the network even away from their main workstations. And this is definitely a cost savings from a business perspective. We also have to consider the scenario of the small office, home office. As an IT professional, you may yourself have more than one computer at your home. And if you do, these computers are most likely connected together so that you can share your files and your printers or your connection to the internet or whatever the case may be. This type of configuration is also utilized by many businesses that have only a few employees. These businesses do have the need for the sharing of information between all of their users and a single internet connection for efficiency and for greater productivity. For these applications, what's known as a SOHO, or small office home office, a wireless LAN is a very simple and effective solution in this environment. Wireless SOHO devices are especially beneficial when office workers want to share a single internet connection. The alternative, of course, is running wires throughout the office to interconnect all of the workstations and printers and so forth. But many small offices are just not outfitted with pre-installed Ethernet ports, and only a very small number of houses are wired for Ethernet networks as well. So trying to retrofit these places with Cat5 cabling usually results in creating unsightly holes in the walls and in the ceilings, and also incurring additional expense, which is really unnecessary. With a wireless LAN, users can be interconnected easily and neatly, and with a minimal amount of effort. We also have to consider what will happen in a business scenario where we do have mobile offices. Mobile offices do exist in many different varieties, and really one of the best examples is that of the university that has remote classrooms. They allow the users to pack up their computer equipment quickly and to move to another location without the extensive complications of wired networks. Due to overcrowded classrooms in some cases, many schools actually use mobile classrooms today. These classrooms usually consist of large, movable trailers that are used while more permanent structures are built, or even used permanently in certain situations. The opposite side of the coin in this case is that we would have to provide permanent facilities where underground cabling or even aerial cabling would have to be installed at a much greater expense. Wireless LAN connections from the main school building to the mobile classrooms do allow us to have much more flexible configurations at a fraction of the cost of actually installing hardwired cable. Temporary office spaces also benefit from a very similar type of networking. We use wireless LANs, and as that company grows, they often find themselves with a shortage of office space and really need to move some workers to a nearby location, such as an adjacent office or even to another floor of the same building. Installing Cat5 or fiber optic cabling between these facilities is definitely not going to be cost-effective for a small office. Usually the owners of the building do not allow for the installed cables to be removed when they leave either. But with a wireless network, the network components can be easily packed up and moved to the next location very quickly and very easily. There's also other groups that might use movable networks effectively, such as maybe sports events like the Super Bowl or the Olympics. These types of organizations, these types of events actually use wireless networks because they are so easy to pack and go. Wireless LANs are very well suited to these types of environments. Even hospitals and healthcare facilities benefit greatly from wireless LANs. The other thing to think about with this type of networking is how valuable it is for any of the individuals that work in these mobile offices to be able to connect and use their wireless devices. In the case of hospitals, doctors can actually use wireless PDAs to connect to the networks and mobile diagnostic carts that nurses can move from room to room to connect the patient to the network. Wireless networks allow the doctors and nurses to perform their job much more efficiently using these new devices and associated software. And as the popularity of wireless networks increases, the software vendors continue to produce new software applications that directly integrate with wireless, especially messaging software and security that involves network admission control for security purposes, being able to isolate your network from viruses and worms and performing quarantines and things like this. All the software vendors out there are very interested in the success of wireless networks and are continuing to improve their software offerings. I was just listening to the radio. That's the magic of wireless networking as well. The same types of radio frequencies that are used to broadcast your favorite radio station are used to interconnect wireless networks. This is paramount. This is one of the things that you're going to have to master to be properly trained in wireless LANs, is to understand RF and how it works. What is RF? What exactly is radio frequency? Well, actually, they're very high-frequency AC signals that are passed along some sort of a copper conductor and then radiated into the air via an antenna. An antenna will transform a wired signal to a wireless signal and vice versa. When the frequency AC signal is radiated into the air, it forms radio waves. And these radio waves propagate or move away from the source, which is the antenna, in a direct straight line in all directions at once. If you could imagine dropping a rock into a still pond and watching the concentric ripples flow away from the point where the rock hit the water, then you have an idea of how RF behaves as it's propagated from the antenna itself. Understanding the behavior of these propagated RF waves is a very important part of your understanding of why and how wireless local area networks function. Without this base of knowledge, an administrator would not be able to properly locate the antenna, would not understand the proper installation locations of equipment, and would not understand how to troubleshoot a problematic wireless LAN. So it is paramount that we do understand radio frequency. Now, to be able to do so, we are going to have to understand a variety of radio frequency behaviors: gain, loss, reflection, refraction, diffraction, scattering, and absorption. All of these elements actually make up the way that radio frequency behaves, and they all have to be fully understood for us to properly understand where our equipment needs to be placed and how our installation is going to be carried out for our network environment. If we accidentally place an antenna in the wrong place, we can deal with all kinds of outside interferences. We can, of course, disrupt somebody else's radio transmissions, or we just might not get the throughput that we desired. So understanding these RF behaviors is going to be one of the key elements of this series. We're going to continue to go back and forth with all of these RF behaviors as we proceed through actual implementation of our wireless LANs. Radio frequency is sometimes referred to as smoke and mirrors because radio frequency seems to act very erratically and inconsistently under given circumstances. Things as simple as a connector not being tight enough or a slight impedance mismatch on the line can actually cause very erratic behaviors and undesirable results with RF. So the first term that we have to get used to is what's known as gain. Gain is the term that is used to describe an increase in an RF signal amplitude. Gain is usually an active process, meaning that an external power source, such as an RF amplifier, is used to amplify the signal, or a high gain antenna is used to focus the beam width of a signal to increase its amplitude. Being able to measure and compensate for loss in an RF connection or circuit is very important because radios have a received sensitivity threshold. A sensitivity threshold is actually defined as the point at which a radio can clearly distinguish a signal from background noise. Since a receiver's sensitivity is finite, the transmitting station must transmit a signal with enough amplitude to be recognizable at the receiver. If losses occur between the transmitter and receiver, the problem must be corrected either by removing the objects that are causing the loss or by increasing the transmission power. The second component that we have to look at is what's known as reflection. Reflection occurs when a propagating electromagnetic wave impinges upon an object that has a very large dimension when compared to the actual wavelength of the propagating RF wave. Reflections occur from the surface of the Earth as well as a variety of man-made objects such as buildings, walls, and so forth. If the surface is smooth, the reflected signal may remain intact, though there is some loss due to absorption and scattering of the signal. RF signal reflection can cause serious problems for wireless LANs, and it's something that has to be very well understood. The reflection of the main signal from many objects in the area of the transmission is referred to as multipath. Multipath can have severe adverse effects on a wireless LAN, such as degrading or canceling the main signal and causing holes or gaps in the RF coverage areas. Surfaces such as lakes, metal roofs, metal blinds, doors made out of metal, and others can cause very severe reflection and hence create multipath. Reflection of this magnitude is never desirable and typically requires very special functionality, such as antenna diversity within the wireless LAN hardware to be able to compensate for it. Besides reflection, we also have what is known as refraction. Refraction describes the bending of a radio wave as it passes through a medium of different density. As an RF wave passes into a denser medium, like a pool of cold air lying in a valley, for instance, the wave will be bent such that its direction will change. When passing through such a medium, some of the wave will be reflected away from the intended signal path, and some will be bent through the medium into another direction. Refraction can become a problem for long-distance radio frequency links. As atmospheric conditions would change, the RF waves may actually change direction, diverting the signal away from the intended target. Another major component of RF behavior is what's known as diffraction. Diffraction occurs when the radio path between the transmitter and the receiver is obstructed by a surface that has sharp irregularities or an otherwise rough surface. At high frequencies, diffraction, very much like reflection, will depend upon the geometry of the obstructing object and the amplitude, phase, and polarization of the incident wave at the point of diffraction. Diffraction is commonly confused with and improperly used interchangeably with the term refraction. Now, you need to be very careful to never confuse these terms. Diffraction describes a wave bending around an obstacle, whereas refraction describes a wave bending through some sort of a medium. Taking the rock in the pond example, consider a small twig sticking up through the surface of the water near where the rock hit the water. As the ripples hit the stick, they would be blocked to a small degree, but to a larger degree, the ripples would bend around the twig. This would show how diffraction would act with obstacles in its path, depending upon the makeup of the obstacle. If the object was very large or jagged enough, the wave might not bend, but rather it would be blocked. Diffraction is the slowing of the wave front at the point where the wave front strikes an obstacle, while the rest of the wave front maintains the same speed of propagation. Diffraction is the effect of waves turning or bending around the obstacle. Another example, consider a machine blowing a steady stream of smoke. The smoke would flow straight until an obstacle entered its path. Introducing a large wooden block into the smoke stream would cause the smoke to curl around the corners of the block, causing a noticeable degradation in the smoke's velocity at that point, and a significant change in direction. And that's probably the best definition of diffraction that you can use. Beyond diffraction, we also have to identify what is going to happen when our radio frequency wave actually hits jagged objects. This is known as scattering. Scattering occurs when the medium through which the wave travels does consist of objects with dimensions that are very small compared to the wavelength of the signal itself. The number of obstacles per unit volume also may be large. Scattered waves are normally produced by very rough surfaces, very small objects, or by other very small irregularities in the signal path. Objects such as trees and bushes, street signs, and lampposts would be excellent outdoor examples of things that may cause scattering. Scattering can take place in two primary ways. First, scattering can occur when a wave strikes an uneven surface and is reflected in many different directions simultaneously. Scattering of this type yields many very small amplitude reflections and destroys the main radio frequency signal. Dissipation of an RF signal may occur when an RF wave is reflected off of sand, rocks, or other jagged surfaces. When scattered in this manner, RF signal degradation can be significant to the point of intermittently disrupting communications altogether or even causing complete signal loss. The second type of scattering can occur as a signal wave travels through particles in the medium, such as heavy dust content, such as during a very heavy storm. In this case, rather than being reflected off of an uneven surface, the RF waves are individually reflected on a very small scale off of the tiny particles in the air. Another component that you always have to consider with radio frequency is that of absorption. Absorption occurs when the radio frequency signal strikes an object and is absorbed into the material of the object in such a manner that it does not pass through, reflect off, or bend around the object. Now, in the case of absorption, you can actually lose the power of your RF signal. So you must be aware of the types of objects that can actually absorb radio frequency signals and understand how to avoid having them in your direct signal path. The other major concept that needs to be understood when identifying RF behaviors is understanding the concept of the voltage standing wave radio, or VSWR. VSWR is actually something that occurs, and it does so when there is mismatched impedance, which is resistance to current flow measured in ohms. Anytime we have mismatched impedance between devices in an RF system, mismatched in this context would mean that one piece of equipment has a greater or lesser impedance than the piece of equipment to which it's connected to. VSWR is caused by an RF signal reflected at a point of impedance mismatch in the signal path. VSWR causes what is known as return loss, which is defined as the loss of forward energy through a system due to some of the power being reflected back towards the transmitter. If the impedances of the ends of a connection do not match, then the maximum amount of the transmitted power will not be received by the antenna. When part of the RF signal is reflected back towards the transmitter, the signal level on the line varies instead of being steady, which is obviously not a good thing when we're dealing with wireless LANs and connectivity. This variance is actually what they call the indicator of VSWR. To illustrate this exact point, you've probably done this yourself while washing your car or doing some outside work, where the first hose that you tried to use to perform the job was not long enough, so you actually used a coupler to attach a second garden hose. Now imagine if you were to send water down those two connected garden hoses. If both garden hoses were exactly the same diameter, the same size, water would flow through them seamlessly. But if the hose connected to the faucet was larger than the next hose down the line that you connected to, of course, extend your range, there would be back pressure on the faucet, and even at the connection between the two hoses in this example. Now, here you can see that back pressure can actually have a negative effect, and not nearly as much water is going to be transferred to the second hose, due to the fact that we have a higher impedance on down the line. In this case, we would have to make sure that our hoses would match and were screwed together properly to prevent the backlog of water. This is what's known as return loss, and this is actually the indicator of VSWR. Mismatched impedances on our circuit path can actually cause this. Now, there is something that you can do to express VSWR measurements to identify if you're within range. VSWR is actually a ratio, so it is expressed as a relationship between two different numbers. A typical VSWR ratio would be 1.5 to 1. The two numbers relate the ratio of impedance mismatch against a perfect impedance match. The second number is always 1, representing the perfect match, which is why the first number varies. The lower the first number, closer to 1, the better impedance matching your system has. For example, a VSWR of 1.1 to 1 is a lot better than a 1.4 to 1 VSWR. A VSWR impedance measurement of 1 to 1 would denote a perfect impedance match, and no voltage standing wave would be present in the signal path at all. Well, very important that we understand not only what the measurement's all about, but also what the effects are. Excessive VSWR can cause very serious problems in an RF circuit. Most of the time, the result is a marked decrease in the amplitude of the transmitted RF signal. However, since some transmitters are not protected against power being applied, or in fact returned to the transmitter output circuit, the reflected power can actually burn out the electronics of the transmitter. VSWR's effects are evident when transmitter circuits burn out or power output levels are unstable, and the power observed is significantly different than what the expected power was supposed to be. The methods of changing VSWR in a circuit include proper use of proper equipment. What that's going to mean is that you actually use matched equipment, potentially from the same vendor at either end. Tight connections between cables and connectors, use of impedance-matched hardware throughout, and use of high-quality equipment with calibration reports where necessary are all very good preventative measures against VSWR. VSWR can be measured with very high accuracy using things such as SWR meters, but this measurement is beyond the scope of what we're doing in this particular series, and it's definitely going to be a more advanced task, something that an expert level would do. But to give you some basic solutions to VSWR is going to be a good idea at this level. To prevent the negative effects of VSWR, it is imperative that all cables, all connectors, and all devices have impedances that match as closely as possible to each other. Never use 75 ohm cable with 50 ohm devices, for example. But most of today's wireless LAN devices do have an impedance of 50 ohms. It's still recommended that you do check each device before implementation, just to make sure that they're very, very close. Every device from the transmitter to the antenna must have impedances matching as closely as possible, including all of your cables, all of your connectors, any antennas and amplifiers, attenuators, even the transmitter output circuit and the receiver input circuit need to have as close as possible of an impedance match. And that will help you to eliminate the effects of VSWR. And it is all conceptual right now. Right now, we've just got to understand the behaviors of RF so that we know what these different terms are. The focus is understanding the concepts behind what gain is and loss and reflection, refraction, all these different things, so that later on, when we actually go to put in a wireless LAN implementation, we understand how these different behaviors will actually affect us, either positively or negatively in our wireless LAN design. To be able to broadcast and to properly receive radio frequency signals, we are going to have to fully understand the concepts of antennas, knowing exactly what different types of antennas can do for our transmissions and, of course, our reception, and also understand antenna diversity. Let's go ahead and take a look at some basic principles of radio frequency antennas. One thing to realize about antenna principles is that it's not really going to be necessary for a wireless LAN administrator to thoroughly understand antenna design in order to administer your network. However, there are a couple of key factors that you want to understand that are real generic about antennas. First and foremost, antennas convert electrical energy into RF waves in the case of a transmitting antenna, or RF waves are converted back into electrical energy in the case of a receiving antenna. In addition, the physical dimensions of an antenna, such as its length, are directly related to the frequency at which the antenna can propagate waves or receive propagated waves. There are going to be some specific things that we will want to understand, though, in administering license-free wireless LANs. First and foremost is line of sight. We need to understand the concept behind line of sight and how we can actually use this effectively. And when it comes to line of sight, we need to understand what the effects are of the Fresnel zone, what this is going to provide for us in a line of sight connection. In addition, understanding what obstruction will do to the radio frequency path when being generated and received by antennas, antenna gain through focusing our beam widths, the intentional radiator, and finally, equivalent isotropically radiated power, or EIRP. These are going to be the main elements of understanding the basic principles of antennas. The first thing that we need to focus on is that of line of sight. With visible light, visual line of sight, also called simply LOS, is defined as the apparently straight line from the object in sight, or the transmitter, to the observer's eye, which is the receiver. The LOS is an apparently straight line because light waves are subject to changes in direction due to refraction, diffraction, and reflection in the same way as radio frequency transmissions. Radio frequency works very much the same way as visible light within wireless LAN frequencies, with one major exception. RF, line of sight, can also be affected by blockage of the Fresnel zone. Imagine that you're looking through a 2-foot-long piece of pipe. Imagine further that an obstruction were blocking part of the inside of the pipe. Obviously, the obstruction would block your view of the objects at the other end. That simple identification shows how radio frequency works when objects block the Fresnel zone, except that with the pipe scenario, you can still see the other end to some degree. With radio frequency, that same limited ability to see translates into a broken or a corrupted connection. Radio frequency line of sight is very important because RF does not behave exactly in the same manner as visible light. And that leads us right into the Fresnel zone. A consideration when planning or troubleshooting your RF link is the Fresnel zone itself. The Fresnel zone occupies a series of concentric ellipsoid-shaped areas around the line of sight path. The Fresnel zone is important to the integrity of the radio frequency link because it does define an area around the line of sight that can introduce radio frequency signal interference if blocked. Objects that are in the Fresnel zone, such as trees or hilltops, even buildings, can diffract or reflect the main signal away from the receiver, changing the radio frequency's line of sight. These same objects can also absorb or possibly scatter the main radio frequency signal, causing degradation or even complete signal loss. What needs to be done is to calculate what the radius of the Fresnel zone will be at its widest point. What we'll use is an industry standard formula to do so, where in this case, D is going to be the link distance in miles, F is the frequency in gigahertz, and the answer R is going to be calculated in feet. For example, we'll pretend there's a 2.4 gigahertz link 5 miles or 8.35 kilometers in length. The resulting Fresnel zone would have a radius of 31.25 feet, or 9.52 meters. What we've got to make sure of is that nothing blocks the Fresnel zone. It must be clear of obstruction if we want to have a guaranteed line of sight path. Now, considering the importance of the Fresnel zone clearance, it's also important to quantify the degree to which the Fresnel zone can be blocked itself, since an RF signal, when partially blocked, will bend around the obstacle to some degree. Some blockage of the Fresnel zone can occur without significant link disruption. Typically, when blocking the Fresnel zone, 20 to 40% Fresnel zone blockage introduces little to no interference into the link. It is always suggested to try to err to the conservative side, allowing no more than 20% blockage of the Fresnel zone if possible. Obviously, if trees or other growing objects are the source of the blockage, you may want to consider designing the link based upon 0%. If the Fresnel zone of a proposed RF link is going to produce more than 20% blockage, or if an active link becomes blocked by new construction or tree growth, raising the height of the antennas will usually alleviate the problem. A question commonly asked about the Fresnel zone when using indoor wireless LAN equipment such as PC cards and access points is how blockage of the Fresnel zone affects indoor installations. In most indoor installations, RF signals pass through, reflect off, and refract around walls, furniture, and other obstructions. The Fresnel zone is not encroached upon unless the signal is partially or fully blocked. This is sometimes the case, but is rarely noticed due to most wireless users being completely mobile. In a mobile environment, the Fresnel zone is constantly changing, so the user normally dismisses it thinking that the coverage is simply bad where they're located, giving no thought to why the coverage is bad, and typically what they'll end up doing is just simply moving. And once they moved, of course, the Fresnel zone is no longer blocked, and everything is back to normal. But another major consideration with antennas is the gain of the antenna itself. An antenna element, without the amplifiers and filters typically associated with it, is a passive device. There is no conditioning, amplifying, or manipulating of the signal by the antenna element itself. The antenna can create the effect of amplification by virtue of its physical shape. Antenna amplification is the result of focusing the RF radiation into a tighter beam, just as the bulb of a flashlight can be focused into a tighter beam, creating a seemingly brighter light source that sends the light further. The focusing of the radiation is measured by way of what are known as beam widths, which are measured in degrees horizontal and vertical. A good example of this is an omnidirectional antenna that has a 360-degree horizontal beam width. By limiting the 360-degree beam width into a more focused beam of, let's say, 30 degrees at the same power, the RF waves will be radiated further. This is how patch, panel, and Yagi antennas, all of which are semi-directional antennas, are designed. Highly directional antennas take this theory a step further by very tightly focusing both the horizontal and the vertical beam widths to maximize distance of the propagated wave at a lower power. Another major component that we need to understand is the intentional radiator. As defined by the FCC, an intentional radiator is a radio frequency device that is specifically designed to generate and to radiate RF signals. In terms of hardware, an intentional radiator will include the RF device and all cabling and connectors up to, but not including, the antenna itself. Any reference at all to power output of the intentional radiator always refers to the power output at the end of the last cable or connector, as would be shown in this particular example. And it's right before the antenna actually takes over in the signal path. For example, consider a 30 milliwatt transmitter that loses 15 milliwatts of power in the cable and another 5 milliwatts from the connector at the antenna. The power at the intentional radiator would be only 10 milliwatts. As an administrator, it's going to be your responsibility to understand the FCC rules relating to intentional radiators and their power output. Understanding how power output is measured, how much power is allowed, and how to calculate these values are all things that we're going to cover in this series. FCC regulations concerning output power at the intentional radiator and EIRP are found directly in the FCC document, Part 47 CFR, Chapter 1, Section 15, dated October 1st of 2000. You can look this right up on the FCC website, be able to take a look at exactly what the intentional radiator limitations are. In addition to the intentional radiator, we need to discuss what is known as the equivalent isotropically radiated power, or EIRP. Now, this is the power that is actually radiated by the antenna element itself, after whatever signal loss we might have incurred during the transit path, right before the antenna. This concept is also important because it is regulated by the FCC, and because it's used in calculating whether or not a wireless link is going to be viable for use. EIRP takes into account the gain of the antenna. Now, when we take a look at an example, let's say that a transmitting station uses a 10 dBi antenna, which amplifies the signal tenfold. It is fed by 100 milliwatts from the intentional radiator. The EIRP is now 1,000 milliwatts, or 1 watt. The FCC has rules defining both the power output at the intentional radiator and the antenna element itself. And these are things that we have to look into to verify that we're not violating any FCC regulations. Failure to comply with FCC rules regarding power output can subject the administrator or the organization, or possibly both of you, to both legal action and fines from the FCC. And to the degree that you understand antennas, understand the proper gain and so forth, is really going to allow you to really focus your wave propagation throughout your radio frequency environment. Now, it is going to be important as we proceed through the series that we take everything that we've learned and actually apply this to real scenario. And that does mean that you are going to have to double check your FCC regulations and make sure that you comply. For you to properly understand to what degree you're going to be able to propagate radio frequency waves through your antenna, it is very important to understand radio frequency mathematics. And that means that we're going to need to very fully understand a few units of measure which are used to calculate our power properly when we're actually transmitting radio frequency signals. Now, all of this is going to have to do with the wave propagation through the antenna itself and what is actually received on the other side. There are going to be 4 very important areas of power calculation in a wireless LAN that need to be understood for radio frequency mathematics to be mastered. First and foremost is the power at the transmitting device. the loss and the gain of connectivity devices between the transmitting device and the antenna, which will include cables, connectors, amplifiers, attenuators, and splitters. And then power at the last connector before the radio frequency signal enters the antenna, which is the intentional radiator. And then finally, power at the antenna element itself, the EIRP. Each of these areas will help you to determine whether RF links are going to be viable without overstepping power limitations that have been set by the FCC. Each of these factors has to be taken into account when planning a wireless LAN, and all of these factors are related mathematically to one another. What we're going to do is to go through the units of measurement that are used to calculate power output when configuring your wireless LAN devices, and this is going to lend itself to the appropriate wave propagation that we have from our antennas. The first thing that we have to discover are the units of measure which are used in radio frequency transmissions. There are going to be a few standard units of measure that a wireless network administrator should be familiar with in order to be effective in implementing and in troubleshooting your wireless LAN. We need to make sure that using examples of these units of measures, you can fully understand how to put them to use, as well as some sample math problems so that you do have a solid grasp of what is required as part of the administrator's job tasks. If you are planning on certification, you can expect to get some simple mathematical calculations as part of your exam that will verify that you have these concepts solidified in your mind. The first thing that we have to identify are watts. This is actually the basic unit of power. A watt is defined as 1 amp of current at 1 single volt. As an example of what these units mean, think of a garden hose that has water flowing through it. The pressure on the water line would represent the voltage in the electrical circuit. The water flow would represent the amperes, the current, which is flowing through the garden hose. Think of a watt as the result of a given amount of pressure and a given amount of water in the garden hose. 1 watt is equal to an ampere multiplied times a volt. A typical 120 volt plug-in nightlight is about 7 watts as an example. On a clear night, this 7 watt light may be seen 50 miles away in all directions. And if we could somehow encode information, such as with Morse code, we would have a wireless link established. Remember, we are only interested in sending and receiving data, not illuminating the receiver with RF energy as we would illuminate a room with light. You can see that relatively little power is required to form an RF link of very great distances. Here only 7 watts could be seen 50 miles. Now the FCC allows only 4 watts of power to be radiated from an antenna in a point-to-multipoint wireless LAN connection using an unlicensed 2.4 gigahertz spread spectrum equipment. 4 watts doesn't seem like very much, but it's enough to send a clear radio frequency data signal for miles and miles. Another unit of measure that's very important is the milliwatt. Now when implementing wireless LANs, power levels as low as a single milliwatt, which is 1/1000th of a watt, can be used for a small area. And power levels on a single wireless LAN segment are rarely above 100 milliwatts. This is enough to communicate up to half a mile in optimum conditions. Access points generally have the ability to radiate anywhere from 30 to 100 milliwatts of power, depending upon the manufacturer. It is only in the case of point-to-point outdoor connections between buildings that power levels above 100 milliwatts would be used. Now, most of the power levels that are referred to by network administrators will be in the calculation of milliwatt or in dBm. These two units of measurement both represent an absolute amount of power and are both industry standard measurements, which are accepted by most vendors. You'll actually see either one of these calculations, depending upon the hardware vendor, actually printed on their equipment. The other major unit of measure that we have is the decibel itself. Now, when a receiver is very sensitive to RF signals, it may be able to pick up signals as small as 1/1000th of a watt. Other than that, it's obviously numerical meaning. This tiny little number has little intuitive meaning to the normal person and will likely be ignored. Or maybe it's even misunderstood. This is where decibels come in. Decibels allow us to represent these incredibly small numbers by making them much more manageable and understandable. Decibels are based upon a logarithmic relationship to what we've looked at already, which is watts. Now, concerning radio frequencies, a logarithm is an exponent. A logarithm is an exponent to which the number 10 must be raised to reach some given value. On the linear watt scale, you can plot points of absolute power, Absolute power measurement refers to the measurement of power in relation to some fixed reference. On most linear scales, such as watts or degrees or Kelvin, miles per hour, these types of things, the reference is always fixed at 0, which usually describes the absence of the thing measured. 0 watts would equal no power. 0 degrees Kelvin, which would equal no thermal energy. Of course, 0 miles per hour would equal no movement. But on a logarithmic scale, the reference cannot be 0, because the log of 0 does not exist. Decibels are a relative measurement unit, unlike the absolute measurement of milliwatts. Thus, we're going to have to understand what the gain and loss measurements actually are when we're dealing with power gains in radio frequency signals. Power gain and loss are always measured in decibels, not in watts, because gain and loss are relative concepts, and a decibel is a relative measurement. Gain or loss in an RF system may be referred to by absolute power measurement, such as 10 watts of power, or by a relative power measurement, such as half of its power. Losing half of the power in a system corresponds to losing 3 decibels. So if a system loses half of its power, it would actually be minus 3 decibel. Then loses half again would be another 3 decibel. Then the total system loss is 3/4 of the original power. Half first, then quarter, which is half of half. Clearly, no absolute measurement of watts can quantify this asymmetrical loss in a meaningful way. That's what decibels are designed to do. Basically, minus 3 decibels indicates that half the power in milliwatts has been lost. Plus 3 decibels doubles the power in milliwatts. Minus 10 is 1/10 of the power in milliwatts, and plus 10 decibels is 10 times the power in milliwatts. Now that seems like it would be pretty easy, but you wonder, are there other numbers in this logarithmic scale? There actually is not. These two numbers, your 3s and 10s, are what are so important for the purposes of understanding radio frequency gain and loss. And these are actually the numbers by which you would be tested if you were actually certifying in this area. Always remember, half and double, 1/10 and 10 times. That's how your -3, +3, -10, and +10 directly relate to the way that our gain and loss is calculated. We can actually use these quick references almost all of the time when we're dealing with RF math. And these quick references are always known as the 10s and the 3s. When calculating power gain and loss, you can almost always divide an amount of gain or a loss by 10 or 3 or both. And these values can give the administrator the ability to quickly and easily calculate the radio frequency loss and gain with a fair amount of accuracy without the use of a calculator. In the case where use of this method is not possible, there are conversion formulas that can be used for these calculations. You can get those right off of the internet. Another important point to understand is that gains and losses are additive. If an access point were connected to a cable whose loss was -2 decibels, and then a connector whose loss was -1, then those loss measurements would be additive and yield a total of -3 decibels of loss. Some of these calculations can be used to quantify exactly what your gain and loss is in your radio frequency conversion. One of the major factors in the absolute reference points that we use to relate the logarithmic dB scale to the linear watt scale is known as dBm. Now, dBm is actually a very easy thing to calculate. What you're looking at is 1 milliwatt is roughly equivalent to 0 dBm. The M in dBm simply refers to the fact that the reference is 1 milliwatt. And therefore, a dBm measurement is a measurement of absolute power. The relationship between the decibel scale and the watt scale is estimated using some basic rules. Plus 3 decibels will double the watt value. As you can see, if we take 10 milliwatts plus 3 decibels, we get approximately 20 milliwatts. Likewise, a -3 decibel will have the watt value. 100 milliwatts minus 3 decibels gives me approximately 50 milliwatts. Plus 10 decibel will increase the watt value by 10-fold. As you can see, 10 milliwatts plus 10 decibels will give you approximately 100 milliwatts. Conversely, a -10 will decrease the watt value to 1/10 of that value, and so on. These rules will allow a very quick calculation of milliwatt power levels when given certain power levels to begin, when you're looking at gains and losses in both dBm and dB. In this case, the reference point is always the same, but the power levels themselves can move in either direction from the reference point, depending upon where they represent the power gain or the power loss overall. One of the easiest ways to quantify this is to take a look at the decibel charts. Now, decibel charts actually indicate gains and losses, and there are two separate charts, one which represents gains or losses in increments of 10, and one that represents gains and losses in increments of 3. You can see in the top chart, they're represented in 10 decibels, and they're shown at each increment. You can see that a gain of plus 10 decibels from the reference point of 1 milliwatt moves the power to plus 10 dBm, or 10 milliwatts. Conversely, you can notice that a loss of negative 10 decibels moves the power up to negative 10, or 100 microwatts overall. The bottom chart is exactly the same. The same principle applies here. These charts both represent the same thing, except that one is incremented in gains and losses of 3 dB, and the other for gains and losses of 10 dB. They've been separated into two separate charts just so that you can see the difference in the calculations. Using these charts, you're able to easily convert dBm and milliwatt power levels. These charts are available all over the internet for easy conversion when you're dealing with these types of mathematics. Now, the one thing that we have to try to quantify is identifying our gain and loss measurement in decibels, and then being able to convert this to the actual gain of an antenna. Now, this is going to focus on what is known as dBi. The unit of measurement dBi refers only to the gain of an antenna. The I actually stands for isotropic, which means that the change in power is referenced against an isotropic radiator. An isotropic radiator is a theoretical ideal transmitter that produces useful electromagnetic field output in all directions with equal intensity and at 100% efficiency in three-dimensional space. One example of an isotropic radiator is the sun. Really good example. Think of dBi as being referenced against perfection. The dBi measurement is used in RF calculations in the same exact manner as dB. Units of dBi are relative. The calculation works in the same fashion as showing gain measured in dB. A gain of 10 dBi just simply multiplies the input power of the antenna by a factor of 10. And antennas, unless they're malfunctioning, do not degrade the signal at all. So the dBi value is always going to be positive. Considering, as an example, a 10 dBi antenna with 1 watt of power applied, what is the EIRP, the output power of the antenna itself? What you can take is 1 watt plus 10 dBi, which is a 10-fold increase. That's going to give you a grand total of 10 watts of power at the antenna itself. Now, like dB, dBi is a relative unit of measure, and it can be added to or subtracted from the other decibel units. So you want to make sure that you understand how those charts actually apply to this, whether you're measuring decibels or in dBi. They're very much the same. Providing a sample calculation when actually calculating the original power of an access point and what the final power, either gain or loss, is going to be as it leaves the antenna, you can follow a very simple example. In this calculation, we're looking at point A, which you can see is minus 3 decibels. Point B, this connector here, we also lose 3 decibels. Point C, we lose 3 decibels, but at point D, you can see that we gain 12 dBi. Now, if you follow this through and look at our calculations all the way through with each point that this signal must pass through, by the time we finish with the plus 12 dBi at the end, we end up with a grand total of 200 milliwatts of power leaving the antenna itself. Now, although these techniques are very helpful and expedient in some situations, there are times when rounded or even numbers may not be available. In these times, using formulas is going to be the best method of doing RF calculations. Since the decibel unit is a unit of relative power measurement, a change in power level is implied all the time. If the power level is given in dBm, then change in dB is simple to calculate. Here we can see the initial power is equal to 20 dBm. Our final power is 33 dBm. The change in power, we can see power is equal to 33 minus 20. So we actually have plus 13 dB. The value is positive, indicating an increase in power. However, if the power levels are given in milliwatts, the process can actually become much more complicated, as we are going to have to identify our initial power as being 130 milliwatts and our final power as being 5.2 watts. The change in power requires an actual conversion. First to milliwatts, and then to the calculation would be an increase of 16 total milliwatts. So it can become much more complex. One thing to realize is that simple calculations are what are required here, and generally rounding off the numbers are what we're focused on at this level of network administration. As we get in more depth into our expert level and integrator level with our certified wireless areas, that's when we'll start to get into exact measurements and actual mathematical conversions that give us finite numbers for the way that we actually calculate our gains and losses. And of course, it is important that we can at least break down the 3s and 10s and understand watts and decibels and milliwatts and so forth. Remember that anytime you're measuring your connectors and trying to figure out what your absolute power is coming out of your antenna, it's always going to be cumulative. So all those calculations are going to flow through from the original access point all the way to where it actually leaves the antenna, the EIRP. If you can make those calculations, you can of course identify how many milliwatts or possibly even watts are coming out of that antenna. Verify that you are within FCC guidelines before you actually put that into production. Make sure you're not violating any laws. Another major factor that we're going to have to understand when dealing with wireless LANs and being a wireless LAN administrator is that of spread spectrum technologies. Spread spectrum technologies, which significantly widen the bandwidth that we have and also do so at much lower power, can be very beneficial when we deal with different types of wireless links. What we want to do right now is to kind of understand what the concept is behind spread spectrum and understand how we can put it to use for our own wireless networks. Spread spectrum is a communication technique which is characterized primarily by wide bandwidth and utilizing very low peak power. The communication itself uses various modulation techniques in wireless LANs and does possess many advantages over its precursor, which is known as narrowband communications. Spread spectrum signals are noise-like, hard to detect, and even harder to intercept or demodulate without having the proper equipment. Jamming and interference are also going to have a much lesser effect on spread spectrum communication than on narrowband communications. As a comparison, for these reasons, spread spectrum has long been a favorite of the military. However, in order to discuss what spread spectrum is, we must first establish a reference point by discussing the differences between narrowband transmissions and spread spectrum itself. And we have to first understand the concept of narrowband. Narrowband transmission is a communication technology that uses only enough of the frequency spectrum to carry the data signal and no more. It's always been the FCC's mission to conserve as much of the frequency usage as they could, handing out only what was absolutely necessary to get the job done. Spread spectrum is in opposition to that mission since it uses a much wider frequency band than is necessary to transmit the information. This brings us to the first requirement for a signal to be considered spread spectrum. A signal that is spread spectrum when the bandwidth is much wider than what is required to send. Now you'll notice in this graphic the difference between narrowband and spread spectrum transmissions. Notice that one of the characteristics of narrowband is very high peak power. More power is required to send a transmission when using smaller frequency ranges. In order for narrowband signals to properly be received, they must stand out above the general level of noise, which is called the noise floor. And they have to stand out by a significant amount. Because its band is so narrow, a high peak power ensures error-free reception of a narrowband signal. Compelling argument against narrowband transmission, other than the high peak power that's required to send it, is that narrowband signals can be jammed or experience interference very easily. Jamming is the intentional overpowering of a transmission using unwanted signal transmitted on the same band. Because its band is so narrow, other narrowband signals, including just straight noise, can completely eliminate the information by overpowering a narrowband transmission frequency, much like a passing train overpowers a quiet conversation. Spread spectrum technology, on the other hand, allows us to take the same amount of information that we previously would have sent with narrowband and spread it out over a much larger frequency range. A good example of this is if we were to use 1 megahertz at 10 watts with narrowband, but 20 megahertz at 100 milliwatts with spread spectrum. By using a wider frequency spectrum, we reduce the probability that the data will be corrupted or jammed. A narrowband jamming attempt on a spread spectrum signal would likely be thwarted by virtue of only a small part of the information falling into the narrowband signal's frequency range. Most of the digital data would be received error-free. Today's spread spectrum RF radios can retransmit any small amount of data loss due to narrowband interference. While the spread spectrum band is relatively wide, the peak power of the signal is actually quite low. This is the second requirement for a signal to be considered spread spectrum. For a signal to be considered spread spectrum, it absolutely positively must use low power. These two characteristics of spread spectrum, use of a wide band of frequencies and low power, make it look to most receivers as if it were simply a noise signal. Noise is a wide band, low power signal, but the difference is that noise is unwanted. Furthermore, since most radio receivers will view the spread spectrum signal as noise, these receivers will not attempt to demodulate or interpret it, creating a slightly more secure communication as well. This inherent security is what interested the military in spread spectrum technology through the 50s and 60s. Because of its noise-like characteristics, spread spectrum signals could be sent under the noses of enemies using classic communication techniques. Security was all but guaranteed. Naturally, this perceived security of communication was only valid so long as no one else used it, however. If another group were to use the same technology, these spread spectrum communications could be discovered, if not interpreted and decoded. In the 1980s, the FCC implemented a set of rules making spread spectrum technology available to the public sector and encouraging research and investigation into the commercialization of spread spectrum technologies. Though at first glance it seems like the military had lost its edge, it had not. The bands used by the military are very different from the bands used by the public. Also, the military uses very different modulation and encoding techniques than what we would see in most of our applications. And that ensures that its spread spectrum communications are far more difficult to intercept than those of the general public. Since the 80s, when the research began, we started to see spread spectrum technologies now being used in a variety of things, like cordless phones, global positioning satellite systems, digital cellular telephony for, of course, our cell phones, personal communication systems, or PCSs, and now we're starting to see this become ever more present in our wireless local area networks, or wireless LANs. We're also seeing a lot of amateur radio enthusiasts are now beginning to experiment with spread spectrum technologies for many of the same reasons. One of the things that we need to focus on, though, as administrators is that, well, since we're really dealing with personal communications and wireless LANs, mostly, we also have to think about some other applications. Beyond just the wireless LAN implementation, wireless personal area networks, metropolitan area networks, and wireless wide area networks are also very viable solutions, and they're all taking advantage of spread spectrum technologies. Wireless personal area networks use Bluetooth technology to take advantage of very low power requirements to allow wireless networking within very short ranges. Wireless WANs and wireless MANs can use highly directional, very high gain antennas to establish long-distance, very high-speed radio frequency links with relatively low power. So all of these are very viable to the wireless LAN network administrator. The first component that we want to make sure we understand is just the basic wireless LAN. Wireless LANs, MANs, and WANs will use the same spread spectrum technologies in different ways. For example, a wireless LAN might be used within a building to provide connectivity for mobile users, or bridges might be used to provide building-to-building connectivity across a campus. These are specific uses of spread spectrum technology that fit within the description of a local area network. The most common use of spread spectrum technology today lies in the combination of 802.11 compliant LANs and 802.15 compliant Bluetooth devices. These two technologies have captured a tremendous amount of market share, and it's ironic that the two function very much differently, but play within the same FCC rules, yet they interfere with each other greatly. Considerable research, time, and resources have gone into making these two technologies coexist, and that's one of the key elements of what our series is all about. Well, wireless personal area networks, wireless PANs as they're known, Bluetooth, the most popular of our wireless PAN technologies, is specified by the IEEE 802.15 standard. Now, the FCC regulations that regard spread spectrum use are very broad, which does allow for different types of spread spectrum implementations. Some forms of spread spectrum introduce the concept of frequency hopping, meaning that the transmitting and receiving systems hop from frequency to frequency within a frequency band at transmitting as they go along the way. For example, Bluetooth hops approximately 1,600 times per second, while home radio frequency technology, which would be a standard WLAN technology, hops approximately 50 times per second. Both of these technologies do vary greatly from the standard 802.11 wireless LAN, which typically hops only 5 to 10 times per second. Each of these technologies also has very different uses in the marketplace, but all of them will fall within the FCC regulations. One example of this is a typical 802.11 frequency hopping wireless LAN might be implemented as an enterprise wireless networking solution, while home radio frequency is only implemented in home environments due to lower output power restrictions by the FCC. Wireless metropolitan area networks is another use of spread spectrum technology, such as wireless links that would span an entire city using high-power point-to-point links to create a network. They fall into the category of wireless MANs, or metropolitan area networks. A lot of times meshing many point-to-point wireless links to form a network across a very large geographical area, but still using the same technologies as the wireless LAN. The main difference between a wireless LAN and a wireless MAN is that most of the time metropolitan area networks use licensed frequencies instead of the unlicensed frequencies typically used with the standard wireless LAN. 802.16 is a great example of a wireless metropolitan area network. Using a licensed frequency, we can extend the range for miles and miles and allow literally thousands of connected users to be connected at very high data rates to a metropolitan area network. The main reason for the difference here is that if you are an organization implementing a wireless metropolitan area network, you want to make sure that you've got control over the frequency range. You don't want any other company to accidentally implement a network which interferes with your frequency. And that's really why wireless metropolitan area networks use licensed frequencies that are actually purchased. The same factor does apply to wireless wide area networks, or WWANs, as well. And as these technologies continue to advance, we're going to start to see more and more of things like the 802.16 and 802.20 standard really come of age, where we can pretty much be connected to whatever network we want all of the time. No matter where we are, no matter how fast we're moving through the city, we're constantly connected to some sort of a wireless network or another. This is fantastic stuff. Now, I challenge you for sure to go out to the internet, take a look at the 802.16 standard, take a look at the 802.20 standard. You'll actually find some direct comparisons between the two that identify what those standards are all about for wireless networking and see how they're going to apply to our networking industry.